So let's look at this topic we're going to cover today: manifest misconceptions, closing the gaps in SCA-based SBOMs. And if that's not the topic, please stay and listen anyway. What we're going to cover is, if I can actually get to the next slide. There you go. So for those who don't know anything about ReversingLabs, we are trusted by 20% of the Fortune 100. They trust our solutions, and a lot of security companies also trust our data so that they can make sure that they are getting the right information about malware. We service many industries: finance, high tech, energy. Right. The thing that's unique about us is how quickly and how accurate our threat and risk analysis is. It is also extremely scalable. Right. We can handle massive volumes of files and actually very huge files, and we'll actually talk about that a bit later. Our Spectra core is a binary analysis solution. So we are looking that deconstructs the files and does the analysis in minutes. We also have the largest threat repository in the world, and we also win lots of awards for our great products. Okay, so for our agenda today, I'm going to talk a little bit about this report that we have recently released, the findings, the implications of incomplete SBOMs, and then walk through some real world examples of what gets missed and why. And then we'll end with a quick how Spectra sure helps these challenges. Okay, so like I said, we released this report, Manifest Misconceptions. It's available on our website. The link is down here if you haven't downloaded it already. So for the methodology, what we did is we took about 40 software packages, and we just wanted to see, well, okay, how many SBOM items do we generate versus how many are declared by the manifests that are also included in the software package. So how we do that is we construct the whole binary. We generate what we call an XBOM, which includes 4 different things. The SBOM, which everyone knows about, a CBOM, SASBOM, and LMBOM. We'll get into what those are later. And then we just compared the number of items that we found that were in the manifests. And the big takeaway is if you're only depending on the software manifests in your package to understand, what you're getting in this thing, you're missing about half the picture. And that's a pretty large number. Dave, is this like a surprising stat for you?
No, it's not. I will say that 50% is maybe about the average, but depending on what the software, what type of software you're analyzing, it could be closer to 100% or closer to 0%, really. Especially if you're using an SCA tool. An SCA tool is very good at kind of reporting open source components and specifically, typically looking at a source, like a GitHub source code repo. But if your software is more complex and there's different parts and pieces coming in, or it's a container, you're delivering your software in a container image, most likely it's going to be not even close to 100%. So it just depends. But yeah, absolutely, this is accurate and from what I've seen.
Great. So let's talk a little bit about why this matters, right? If you can't see it, you can't manage it. I mean, that's as old as IT management. The thing about the SBOMs, one of the reasons why they're so powerful is that if you have, a new incident happening, like the next log4j or a new vulnerability that's reported, you can respond to that much faster because you can know where the risks are, and you can tell whether you're vulnerable or not, or whether you're under attack or not. So if you only have part of the picture, then you're basically digging through everything that you have just to figure that out. And then only after you do that can you actually start mitigating the risk. There are also implications for license compliance, classic open source, commercial software as well, and then regulatory compliance. Now, while the US is doing some strange things with their regs, anyone who is selling in Europe is going to need to think about this because their regs are really specific about wanting to see more, wanting you to understand what is in your software. And then there are also just industry-specific regulations. So your medical devices, for instance, they will always require some sort of SBOM and HBOM, quite frankly.
And I'll just maybe jump in there, Jasmine, that if you're
Mhm.
talking about a medical device, how often is that going to be run on 100% open source? Most likely the odds are zero. So in particular, that requirement, which is very stringent, just looking at a manifest, if there even is one, isn't going to probably do the job.
Okay. So again, a little bit more about why this matters. So the annual Verizon data breach investigations report came out a little earlier this year. And one of the big headlines is that third-party breaches are up 100% over last year. And they only added this category last year based on some of the data that we provided them. It forced them to rethink how they think about third-party software. And what I thought was interesting was this report came out, I don't know, early in the week, Monday or Tuesday. And there was this great quote in there that said, if you were in any other industry and a fundamental flaw was introduced into your supply chain due to defective raw materials, your organization will at least be sending a sternly worded letter to the supplier. And lo and behold, on Friday afternoon that same week, there was a sternly worded letter from JP Morgan. It was an open letter to their third-party suppliers. And they are asking them, hey, take a stronger look and make sure that we know what you're giving us, particularly when it comes to the other services that your software is interacting with. So if you haven't read this or seen this, I encourage you to read it. It's a very interesting letter. Okay, so let's get into some real world examples of what gets missed by these SCA type solutions and why. Okay, so the first example we used, we're looking at what we call Python phantom dependencies. And we're using this particular example. This is an older software version. So again, for every example that we're talking about, they're not representative of the current security posture. We're just using them as examples, either because we've analyzed them before and we kind of know we've blogged about them before. So what's getting missed here is dynamically linked dependencies and components not written in Python. So Dave, can you explain exactly what a dynamically linked dependency is for folks who don't know?
Yeah, just first of all, the screenshot that you're seeing on Jasmine's slide is actually from Spectre Assure, which we provide a larger list of components, but you can also narrow the list in the UI to only those that are specified in the manifest. So I just wanted to mention that what you're saying there on that screenshot is from our product. But yeah, so a dynamically linked dependency is something that essentially a piece of software at runtime can bring in a component or a library that it needs. So it doesn't have to be packaged with the actual software release. I mean, a good example of that is just, a Windows DLL. On Linux, it would be a shared object or a .so. It's a common library used by lots of software. And so instead of bundling that library with every release software package, you can just specify to bring that in at runtime. So that's a dynamically linked dependency. And so
why wouldn't they show up in a manifest exactly?
yeah, so well, specifically, we're looking at Python here, Python package NumPy. It's very popular, especially in ML data science world. So a Python package, when it's released on PyPI, the registry, it can be released in two forms, two different types of form. It can be released just as source code, which is basically just a zipped up of the source. It can also be released as a wheel file. And so in this case, the wheel file actually has some compiled components to it, right? So and a wheel file is nice because when you install a Python package from a wheel file, it actually goes a lot quicker because all of the compilation has already been done. And so why would it need to do compilation? Well, Python, just source code, it doesn't care what platform you're running on, whether it's Linux or Windows or Mac or whatever, but a wheel file does care. So a wheel file, when you build a wheel file as a developer, you have to specify what are you building this for? Are you building it for Windows? Are you building it for ARM? Are you building it for Linux? There's just very specific, and the reason to do that because when you install the package and run it on the server or the endpoint, it has to have those platform-specific binaries and native code, basically. And so that's where the missing piece comes in, because if you're just looking for components and dependencies, looking at the source repo, it won't have these dynamic or these native libraries that are built in a wheel file. So that's the big difference there. Again, a wheel file is typically what open source maintainers release on PyPI. And if you go out there and look at one of these packages, you can go to download files link, and typically you'll see one source file package, which is like a zip file or a tar.gz, but then you'll see a whole bunch of wheel files for all the different platforms that it can run on. So that's the difference, is by analyzing a wheel file, you'll have information about the dynamic libraries, but if you're just looking at the source or the Git repo, you wouldn't have that information.
So as I understand it, it's up until just recently, there wasn't a method for you even to list, what those compiled libraries were anywhere.
All right. Yeah. So so Python, there's a whole specification for how you package a wheel file, and what does it need to include, and what is the format and everything. There was no way up until basically 2 months ago for a maintainer to specify in a wheel file, what additional components are there. So above and beyond the standard source pieces. And so the new wheel file format actually has there's a subdirectory that is defined now called SBOMs. And so when a developer builds a wheel file, they can actually specify a full SBOM for that wheel file within the file itself. So it's in that SBOMs subdirectory. So yeah, so you can see the last bullet here, or the last section. The wheel spec has been updated.
Right, it completely depends on developer adoption. No?
Yeah, exactly. If developers don't adopt this new SBOMs directory and use it, then it won't do anyone any good, really. So it depends a lot on the adoption, and also the millions of packages and all the different versions of all the packages that are out there now don't have it today. So it would definitely be there's going to be a time delay here before that really has any effect.
Yep. So the thing is about that, even with the developer filling in the specs, what that means is that you're inherently trusting that the developer is giving you all the right information, that they're filling it out all accurately, or if they're filling it out at all. And that inherent trust has existed since the first set of software has been delivered, but it's killing us now, because the malicious attackers are taking advantage of that. They expect you to trust whatever you're bringing in from your favorite repository or your favorite vendor, and that leaves you open to their attacks. Right? So okay, let's move on to the next example. Here we have a screenshot of 3CX. This is a thing that was actually compromised, and we have a blog on what we did to analyze that. You can go and look at that whenever you want. But again, this is not anywhere near the state that they are today. You can see that their software bill of materials, 234, not bad, but only 127 of them were actually found in the manifests themselves. So if you were depending on an SBOM based on only the manifest, you're only getting half the picture, but it's a little worse than that because the half of the picture that you're getting, looks completely clean, right? There are no CVEs declared in any of the components that were declared by the manifest. So it's kind of like a double whammy there. Okay. Let's see. So this is a different screenshot. These are the things that, we're not in the manifest. You can see a lot of them are commercial and proprietary components, but they're also the components that actually got compromised. So this is why people were in such a bind when it came to this attack, because they couldn't see anything. I mean, I remember some of those early calls. They're like, yeah, but we can't have malware in there. Look, we have no CVEs. It can't be. And it's only after, we walked through what binary analysis is about, did they begin to see why they were only seeing half that picture. So Dave, here's a question for you. What's the deal with the difficulties in finding just commercial proprietary components or just, malware in general?
Yeah, so this 3CX application is a great example of kind of what I was talking about earlier, where this is not a pure open source type of software. It's a Windows desktop application, what we used to call a thick client application, and there are open source components in it. In fact, it's uses a lot of NPM or Node.js libraries because it's part of it is built on the Electron framework, and so there's a lot of open source components, and that's what's in the manifest. So that's what gets reported in most SCA tools and things like that. But there's also a lot of, in this case, Windows native DLLs and whatnot packaged with the 3CX application for Windows. And so, and also some custom things. So that's what doesn't get reported in the manifest. And so by analyzing the full package, not just looking at the manifest, again, this is a screenshot from Spectre Assure, you get the full details of all those proprietary components, the Windows DLLs that are packaged with the software. And then I should also mention above beyond, since we're one of the best in the world at detecting malware in software, that gets triggered here. And so this was a very well-known supply chain attack from a couple of years ago. And 3CX is kind of like SolarWinds. It was an eye-opening event for them, and they've really tightened up their security controls and really solid from that perspective now. But again, this is not only is it about detecting non-open source components and reporting that in the SBOM, it's also about detecting more than vulnerabilities. It's detecting like purposely introduced malicious code, which is what happened here with the 3CX incident a couple years ago.
Yeah, or it can just be we find evidence of tampering. Hey, this component has some suspicious behaviors. You should really take a look at this before.
Yeah, or there's something wrong with the digital signature. Yeah.
Yeah. So it's like you said, we need more than just the list. We also need to look at what risks are associated with each item in the SBOM. Okay. So again, this is just a summary slide. I'm listing out things that we're missing. Again, like Dave said earlier, tools designed to manage open source components often can't identify the commercial and proprietary code. But the other aspect of this is that attacks can happen late in the SDLC. And I think this is the realization that SolarWinds first brought to the fore, right? And why this is important is because most manifests, why are you creating them? You're creating them early in the SDLC so that you can actually build the thing that you want to ship eventually, right? So that's why this exists, but you need it early. So you get this picture of what you expect to be in the software. But if you're having these late stage attacks, the SolarWinds, the Cloud Coves, I mean, the source code wasn't, compromised early. The dependencies weren't compromised early. All of this happened after the build. The package was modified. The repository storing the things that people are going to download is modified. The build process itself was modified. So when you see that sort of thing happening, you don't know what's getting put into your final build, right? So, Dave, any other thoughts on what you would need to actually understand what you're delivering to folks, or what you're getting with your software?
It's just I mean, manifests serve a purpose, and they were never intended really for security and securing the software supply chain, but they're important in the development step. And a lot of the manifests are different depending on what kind of ecosystem you're talking about. Like for Python, it may be a requirements.txt, and there's some other options for specifying dependencies of this, piece of code. NPM is package.json or package lock.json, which specifies all the dependencies that are required. And those things are built automatically. Like for a Node.js app, it'd be your NPM tool that builds the package.json. For example, as a developer, if you're in your Node.js project folder and you're typing, you need to bring in a component, you may type npm install the name of the package. And when you do that, that automatically updates the package.json for your project. So it kind of manages that for you. But the thing is, it's only doing it for the npm libraries. It's not considering all the other components that come in. And again, it's like Jasmine said, it's functioning at the build time, so it knows when it's building that software what components need to be included. But these other attacks, these supply chain attacks that have happened and been in the news, I mean, yes, there's malicious open source libraries being pushed out to the registries all the time, and they get taken down very quickly. But it's these more sophisticated attacks that happen kind of like the build system being compromised itself, like happened to SolarWinds. With 3CX, there was a specific attack very late in the development stage, and so when the software get pushed out or released, the software developer missed it, and basically, in the case of SolarWinds, they actually signed their final packages that had the malware in it. So it was like they looked very trustworthy because of that signature, but unfortunately, their build system had been compromised. So yeah, it's just there's a lot of the late stage stuff is not going to get caught because, like we kind of talked about, SCA tools that build SBOMs based on manifests, they look typically at they're looking at the source repo. So that's great. Yeah, I mean, that's one piece of the puzzle, but not the full story.
Another part of the story is that in that packaging step, you're typically adding a whole bunch of other things like installers or help files or, all sorts of other manner of components are being pulled in. And people can still compromise installers. And that installation process still, to this day, I mean, it was just in May, we had another, compromise installation process. I mean, that's at the end, right? So this is one of the reasons why we have this concept of build safe and buy safe, and that, both consumers and vendors or people who are just developing software need to like communicate with each other, because, it, quite frankly, you need that final visibility, right? If I'm looking at the software that I just downloaded from you, and I can see that, hey, there's some strange things in here. This looks like it's been altered in some way that doesn't seem right. I need to be able to share that information back with the vendor or the producer, because they quite frankly just may not know, mean, it completely depends on, what kind of visibility at what point in the SDLC they have. And I can tell you for sure that a lot of people don't have that final build, just let's check this for the worst possible thing that can happen at the end, right?
Yeah, Jasmine, that last incident with the courtroom video recording software, that one was super interesting. The software was called JAVS, JAVS. And I can't remember what it stands for, Justice Audio Video something or other. But the that's a great example where it's a very sort of custom made piece of software, and it wasn't like general purpose use, right? No, regular person wasn't going to download that and start using it. It was specifically for courtrooms and that environment. And so it was a very targeted attack, and the malware actually wasn't caught until people started reporting problems. And that's another example of a supply chain attack. So the developer didn't catch it. It was the customers of that software ended up getting compromised and reporting the problem, and then it made the news. It was, but pretty interesting. It happened about a year ago. Oh yeah, you got a link there.
I have the links there.
Perfect.
So when you get either you can take a screenshot and then go there. Yeah. Let's see. So the last example we're going to kind of cover is this whole idea of, basically how deep can you go? Right. And I took this screenshot just to illustrate, how complex some of these just folders with the files are in. I mean, how many layers deep is this component, right? It's a recorder that's all the way at the end there. So the point there really is that, problems can reside at any depth, right? And I know that when the first executive order came out asking for SBOMs, their requirement was, well, top layer and maybe second, and that'll be good enough. But quite frankly, it isn't. And the more complex your software is, the worse this problem becomes, quite frankly. Okay. So Dave, what does, so we talked earlier about, when I was describing ReversingLabs, we were talking about binary deconstruction and recursive analysis. Can you give us a little description of what that is and why it can find all the way down to, the bottom of the barrel?
Yeah, so that's our core technology here at ReversingLabs, and it's quite honestly what I found super interesting and wanted me make me want to join the company. So our analysis isn't done on source code. We take the binary, and the reason we can do that is we can deconstruct a binary, so break it apart into its pieces, even if it's like a Windows executable or a DLL or an MSI installer. Anything we understand, we have the technology to, I mean, it's not reverse engineering, but it's deconstructing into its individual pieces. So, I mean, a zip file would be your most obvious example. Like, you can obviously deconstruct a zip file because it's just, compressed, a bunch of other files compressed together in a single file. So think of that. We can do the same for almost any type of binary file that you throw at it. And so but it doesn't just stop at one level. Once it's deconstructed, say the initial file is deconstructed into 20 other files, we start deconstructing those as well. So it's recursive. And that's where you get these very deep multi-layer sort of files embedded very deep in a binary that we can find. So, and what's so nice about this complex binary analysis that we do is we don't require the binary to be compiled in a certain way with certain flags or anything like that. Literally, you just give it to the scan engine. We figure out what it is and start ripping it apart, or deconstructing is the proper term. And so it's also very fast. So it's not a dynamic analysis, it's all static. but it happens recursively, it happens fast, and it allows us to identify vast amounts of information about every file in that binary, or whatever it is. It doesn't have to be a software binary. We also can deconstruct container images. So, so we can do the same for container images, even VM disk images. Like, give us an OVA or a VMDK. We will do the same for that. I mean, a very large file. So when I first joined, the max file size was 10 gigabytes. We had customers wanting to scan VM disk images larger than that. And so now we're up to 50 gigabytes in a file size, which if you zip the file before sending it to the scan engine, that brings it down typically even more. And so as long as that initial file that is submitted to the engine is below 50 gigabytes, we can scan it. And so it's very powerful.
I think the problem with most of our competitors is that they'll start skipping files if the thing is too large, right? So, but they don't tell you that what they're skipping. So you have this false sense of security.
Yeah, like the AV vendors, right? They can't scan files over like a few hundred megabytes, I believe. And then even like, say, if you want to download something from like, say, G Drive, if you're on the Google Suite, if the file's too big and you want to download it, Google will tell you, normally we scan this for viruses or malware, but this file's too big, we can't do it. So
yep.
Yeah, a lot of file size limitations out there that we don't really have.
So I had said earlier that the larger things get, the more problematic this issue is. So I was trying to find some real world stats on, the growth of file sizes and the growth of how enterprise applications are growing, and I couldn't find anything. The only people who are talking about it is actually gamers. Now, I'm not a gamer, but I have heard of Call of Duty. And it's pretty amazing when you think about it. When it was released 21 years ago, it was a little over a gigabyte. And the latest one that was released in October last year is, I don't even know how much this is. This is like 1,000 times growth in the 21 years. So if you extrapolate from just your regular game console, which anybody can buy, to enterprise software, you can see what's going to happen, right? And like Dave was saying, I mean, we are seeing files just get larger and larger and more complex. And I say that a lot, and people are like, yeah, Jasmine, what does that look like? So I put together this slide, and I kept the names off to protect the innocent, or not so innocent, just to give you a sense of, how big these things are, right? So we've got two files here that are over 30 gigabytes big. Their SBOMs are wildly different. One is over 100,000 SBOM items. But the also interesting thing is just the artifacts, right? So the things that we wouldn't show up in your SBOM, right? All those help files or PDFs or videos or all sorts of manner of things. I didn't include it here, but there we have a dashboard that just, gives you an illustration of all the different file types you have, and it gets crazy. Okay.
Yeah,
But
one way. Sorry, Jasmine. I was just going to say about the difference between SBOM items and artifacts. Like you said, it's things that are not in an SBOM, like help file. But if you think of like, say, like a Java or a Maven library, which is packaged as a jar and delivered as a jar file. So a jar file would equate to an SBOM item. So it would be a component in the SBOM. But a jar file, it could have hundreds of files within it. They would be Java.class files, so the bytecode for Java, as well as other things like images and or if not necessarily images for a jar file, but so you can think of the jar file as being the SBOM item, but there could be 100 files, which would be artifacts that we would also be able to track and report on and quantify. So that's why the number of artifacts can be so much larger than an SBOM count.
And the thing is, malicious actors can embed malware in anything. I mean, one of our most popular blogs was explaining how malware gets embedded in images and PDFs. Right, so you might think you're safe, but no, those have to be checked too, at least for malware, which is what.
Yeah, like for example, if someone tampered with a jar file and put in a malicious .class, so there's malicious Java code in there. Normally, when we see a jar, we will verify it, and we'll verify it by hash, and we'll say this is a known good jar file. We've seen it before. We know it's safe. That goes back to that 220 terabyte. What was it? 220. Can't remember now, but it was our file reputation database. How large it is, and so we've seen probably every legitimate jar file that has ever been released on Maven. We know what it is, and we recognize it, and we say this is good. However, if someone tampers with that jar and inserts a different jar or modifies one of the class files in it to insert malware surreptitiously, that's going to change the hash of that jar, and we're going to say, hey, there's a jar here. It's nothing, we don't recognize it, and so we want to be able to verify it, and we will flag that as suspicious and a potentially malicious supply chain attack.
Yeah, and another thing that we do is we actually list out all the behaviors that we find in any of the SBOM components or the artifacts. So that's one of the things that would get flagged. Hey, how come this PDF now can actually have functions and do things, right? So it's pretty comprehensive analysis.
Yeah, like that. If the threat actor modified the jar file to it added code to open up a TCP socket, like that's a behavior that the software is capable of doing. Open the TCP socket. We would see that and report on it. So not only would we say, hey, this jar doesn't match any known hash, we would say there's a behavior here that opens up a TCP socket, maybe, and it wasn't there, or it's not in the legitimate jar. So that's the type of detail you can get to with to detect tampering.
So that's about comparing one version to another as well, right, Dave?
Yeah, exactly. Differential analysis, which is really important. I think dev teams should be using differential analysis, on their final software build to see, does everything here look legitimate? Is there anything that we don't understand between why did this change in this version? This behavior wasn't in the previous version. Is that expected or is that not expected?
Particularly if we've listed the behavior as kind of known suspicious, because we do classify certain types of behaviors. For instance, there are some behaviors we only ever see in malware. So even if it's not a recognized malware family, if we see that particular behavior, we know something bad is about to happen.
Yeah, and we'll surface that in the report to highlight it.
Okay, so that's the end of our of the examples that I have. So this is just a summary slide talking about the things, why it has limitations. Software is getting more complex. The supply chain is getting more complex. Most tools are hyper-focused on open source components, but there's so much more to worry about. And manifest scanning, a lot of the time, just depends on this inherent trust model. You're inherently depending on the developer to have taken the time to fill out all the right, modules and all the right information, and that they actually know what is in every single thing that's going into their software. And that's a lot of pressure to put on one team. Right? And then finally, yes, manifests are created early. They're needed for a specific task. They were never really designed to do what we're asking them to do now. So those are the things. So I have some slides here about how we help. I think we've been kind of talking through this as we've been going through some of the examples, but just as a a visual, in comes the binary, out comes what SBOM, XBOM, and all the risks that we look for. So we talked a lot about malware, we talked about tampering, but we also do find some classic CVEs. And what we do with those vulnerabilities is we try to classify them and prioritize them in a way that makes sense in terms of how risky they are. For instance, if some vulnerabilities, we've seen them exploited in the wild, that should be a higher priority fix than just anything that we find. Similarly, if we know that there's an active malware campaign going on against a specific vulnerability, or some government regulations are requiring that this particular CVE be remediated before they accept the software, then those, again, should be prioritized higher than anything else.
I should clarify here one thing in that our product, if many of you, if you're in the application security world, static application security testing or SaaS tools. So those are designed to find vulnerabilities in first-party code. So that's not what we're doing. So we are looking for known vulnerabilities. We're not looking at the first-party code, like we don't do data flow analysis or control flow analysis. Just wanted to clarify that because there's that side of the vulnerability equation too. Yeah, but I think the other important piece of this is you see XBOM at the bottom there. So Cyclone DX is kind of at the forefront of bill of material standards, and they've introduced quite a few additional bombs. Oh, there you go, Jasmine's got it. And we support 4 of them really now. Well, more if you could talk about VEX, but so SBOM, of course, but also other types of bombs that we support are the software as a service bomb, which looks at your, say, your API endpoints that the software talks to and reports on that. And there's your ML bomb, machine learning bomb, to identify any models that are embedded in the software if they're on Hugging Face, we'll recognize them and report on them. And then cryptography bomb, going to become super important as we go along here towards quantum computing, because there are certain algorithms that should be used that protect or defend against quantum computing. So post-quantum cryptography, or PQC, CBOM is really going to be important as organizations realize they need to shore up their defenses for the quantum computing world. So Spectre sure supports all these today. We're kind of piggybacking off the Cyclone DX standard. Yeah, so that's why you see XBOM. It's not just about SBOM anymore. There's a lot of other bombs.
Yeah, I remember during our product council meeting, a lot of people were interested in both the SaaS bomb and the CBOM, right? Because they've recognized that, yes, you're getting a package of software or a VM that we're going to install in our environment, but it's going to reach out to other services, and as third-party software risk management becomes more important to organizations, they want to have this understanding of the complete risk profile, I guess, of the application, not just what the risks of the components are that are installed, but what services do they depend on, right? And that's the kind of visibility that we get there.
Yeah, in fact, Jasmine, we had a customer in Texas, which is where I'm based, but the state of Texas doesn't allow any government agencies to use any software from ByteDance, TikTok folks, right? There's like a state law basically, and so one of our customers is a Texas state government agency, and so they were very appreciative to see the SaaS bomb, because if they're bringing in software and they're going to run it for the citizens of Texas, they can't have it reaching out to talk to like the TikTok API or any other API offered by ByteDance. The SaaS bomb gives them the visibility when they're checking software to make sure that that's not the case.
And we also provide additional information. We'll tell you whether it's a bi-directional data flow, will tell you if authentication, I don't know why I'm stumbling on that word, is required or not, right? So it's a good way to think about identifying, the more risky services, because if it's not requiring, authentication, then, that could be problematic for you, especially if they're interacting with your data, or you're sending them data into their service. Okay, so I mean, that's pretty much what I have prepared. There are some resources on this page for you to continue learning. You could also use the resources tab on the webinar, and you'll see all the links there, and you can directly link from that. But other than that, floor is open if anyone has any questions.
Yeah, so I'll just say to kind of wrap up things from I kind of talked about one of the reasons I joined ReversingLabs, but the big eye opener for me was, I think, SolarWinds. That happened in 2020, late 2020, because in my application security career, I had always been chasing vulnerabilities, quashing vulnerabilities, and I assume that as long as we're quashing vulnerabilities, then we're going to be safe, right? And then suddenly the SolarWinds supply chain attack happened, and 18,000 organizations got compromised, or they were basically affected by that incident where a SolarWinds update package had been infected and went out to 18,000 customers and got deployed. And those 18,000 organizations, I mean, they were very well-known names like Microsoft and FireEye. I mean, security companies with very solid application security, cybersecurity posture, and yet they still got infected. And so then I realized, oh, wow, we can't just worry about vulnerabilities anymore. We have to worry about software coming in from other organizations that we're running. So that was a big eye opener for me. I just wanted to share that.
Okay, I see a question here about resources, about identifying components that are not in the SBOM. Okay, so a couple of weeks ago, one of my colleagues and I, we did a webinar on SBOM specifically. So that's one of the things you can go take a look at. Since all our webinars are recorded, you'll get all the details from that webinar. Okay. So I think that wraps it up for us. Another webinar done. Appreciate your time and attention. And don't forget to fill out the survey that's going to pop up after the webinar ends. Thanks.
Thank you.